In section 5.4 of James Stewart's calculus textbook, he moves from definite integrals that he's been talking about earlier in the chapter and moves on to indefinite integrals. So thus far we've seen definite integrals of this form. So the integral from a to b of f of x dx. Now the reason why he starts with definite integrals is because the driving force behind the invention of integral calculus is the so-called area problem. How do you find the area underneath a function when it's not something easy like a straight line? And the answer is that you find the sum of as the limit as delta x approaches 0, you have smaller and smaller rectangles underneath it. Basically the sum of as n approaches infinity of small little rectangles under the line, if you remember that from earlier videos and parts of this chapter. And so because you were looking for the area, usually you were looking for the area under a specific interval, say from a to b, and so it was convenient because the integral calculus starts with the area problem. It was convenient to start with the definite integral, where you were looking for the area under a function over a specific interval like from a to b. And accordingly, the solution to a definite integral is a number, namely the amount of space that's under the function over that interval. But there is also such a thing as an indefinite integral. And it's written like this. You just say the integral of f of x dx, and it's not over a specific interval, it's not over a specific space, but it basically creates a function that is the area at any point under that graph. So it is a function into which you could plug any number along the other function, and you would immediately know what the area was at that particular point. I'm speaking a little imprecisely. It's more, again, the limit as delta x approaches 0 of that infinitesimal underneath. But anyway, if you don't understand that, it's not important. Basically, the indefinite integral is a function that allows you to find that, shall we say, area at any one point, not just on a specific interval like from a to b. It'll be more helpful if we look at an example. So here is the indefinite integral of x squared dx. The integral of x squared is going to be x cubed divided by 3, potentially plus a constant. Of course, it could be 0, but basically the fundamental theorem of calculus verifies this for us, that this is in fact the integral, because if you take the derivative of x cubed over 3 plus c, well, the derivative of a constant is 0, so that goes away no matter what that is. And the derivative of x cubed over 3, well, you basically are going to multiply 3 times 1/3, which cancels out, and take it down to the next lowest power, x squared, and so you're left with x squared. And so you can see that in fact, since we end up with x squared when we take the derivative of x cubed over 3 plus a constant, we can see that we have in fact correctly identified the integral of x squared. Now he did this actually in the earlier part of the chapter, but he did it with specific numbers over specific intervals. So earlier in the chapter we were talking about the definite integral, such as the integral from 1 to 3 of x squared dx. And so what we did, we've already been doing indefinite integrals in the earlier part of the chapter. We just didn't call them that. So if you do the definite integral over the interval 1 to 3, first you're going to plug the 3 in to this. 3 cubed is 27, divided by 3 is 9. And then the 1/3, so 9 minus 1/3 is 8 and 2/3. So the solution to the definite integral over the interval from 1 to 3 is 8 and 2/3, a number, whereas the solution to the indefinite integral is a function, and this function can be used to find the, so to speak, area at any point on this, say at 1 or at 3 or at any other point. So the definite integral is about finding the area at a particular interval, and it ends up being a number. The indefinite integral gives you a function that would allow you to find the area at any point. And so that's a brief introduction to the indefinite as opposed to the definite integral.